Hello everyone. It's our pleasure to have Bingzhi here to share about his work on generative quantum machine learning via denoising diffusion probabilistic models. And this work I personally find that it's quite cool because it is kind of like generalize the diffusion model in classical machine learning related to quantum, and then it gives us a new ways to do like generative modeling in quantum, because like previously we only have like quantum circuit board machines or the similar type of models, but this work basically gives us another angle to design generative quantum model uh, for our task at hand. So, Bingzhi, the floor is yours.
Okay, so hello everyone. I'm Bingzhi Zhang from University of Southern California, and I'm very happy here to be at this seminar and to share our work about generative quantum machine learning via denoising diffusion probabilistic models. It's a very recent work, and you can check the link. You can check our paper here if you are interested in more details. And it's in collaboration with Peng Xu from UIUC and Professor Xiaohui Chen and Professor Qintao Zhuang from USC here. And if you have any questions, you can shoot me by by my email address, and we can start about this talk. So first, I will still give an introduction to get everyone here to be familiar with quantum machine learning, quantum computing, and what about generative quantum machine learning here. And then the second part is about the design and the training strategy of the quantum denoising diffusion probabilistic model. Also, I will just call it a QuDDPM, which we proposed here. And the third part is the complexity and the convergence analysis for our QuDDPM model here. The last part is about some applications that we consider to utilize our QuDDPM to do generative quantum machine learning here. And I will end with a conclusion to conclude the whole talk and to give some ideas about the future directions. So quantum computing, we know that the quantum computing goals is always to design and implement a quantum algorithm to solve that classically hard problems. And people believe that currently we are moving from the stage of noisy intermediate scale quantum era, NISQ era, to the fault-tolerant quantum computing era. And there's also a lot of experimental platform people have come up with and to really build a quantum computer on these different platforms and to do different quantum computing tasks. So then we ask a very hot topic recently is the quantum neural network or quantum machine learning stuff. So why we need it? So the first answer is that it's very hard to design a quantum algorithm for every problems. And then we can just think about then how should we solve this problem, or we can think about in another way. From the development of classical computer, how do the classical people solve this problem? That you also know that it's very hard to solve every classical problem with a specific classical algorithm. So classical people come up with this idea that, okay, we can design a classical neural network or deep machine learning models. And so we can use it to implement arbitrary classical functions or classical maps in general, or in principle to say. Then we can think, okay, if classical people can do it in this way, then a general way for quantum people to do is to utilize a quantum neural network to mimic arbitrary quantum states or quantum operations from this quantum neural network. And then this is the principal reason why we need this quantum neural network here. So there are a lot of applications for using the quantum neural networks. First is, we all know that it can be applied to solve some combinatorial problems, like using the QAOA algorithm, very famous and well-established work, and to solve the max cut problem, K-set problem, and maximum independent set problem, as shown in this experimental figure here. Also, another idea is to design some quantum neural network models to do some many-body phase classification here. Here, this figure is from the well-known paper about the quantum convolutional neural network, where we can input some ground state, typical ground state of a cluster Hamiltonian, and then there are three different phases, many-body phases of this corresponding ground state due to different order parameters. And from this ground state, the QCN will learn how to make a classification on these different phases and identify where the phase boundary it really is. And another application for the quantum neural network is to use quantum machine learning models to do the quantum sensing here. Here, this paper is about that you have some displacement channels and you want to find the find a classification rule to classify different displacement. Using classical machine learning models, you will have some errors, but the quantum machine learning model can provide you extra precision on this classification and the sensing here. So then let's come to a typical structure idea about what really the quantum neural network it is. First, as we do quantum machine learning, just like classical machine learning, we also have data, but now it's not about the classical data, it's a quantum data. And for quantum data, we just assume that it's encoded into a set of quantum states, and which will form the input of our model here. And our quantum computers then will incorporate a bunch of parameterized quantum gates here. And each gate will have one parameter to be tuned and to implement arbitrary function or quantum operation we want here. So after this parameterized gate, we will perform some quantum measurements on the corresponding qubits, and we will obtain some measurement results, and we will input to calculate the cost function of this from the measurement result. And then the final cost function will be input into this classical computer. And the role of the classical computer is to try to find a way to tune these parameters in the quantum gates such that we can decrease the corresponding loss function here. And then we will use this updating rule to update all the parameters in the parameterized quantum circuit and repeat this process. So until the end of these training loops, we will end with the minimum loss function, hopefully. And finally, the output of this quantum neural network will give us either a quantum states, optimal quantum states, or a probability distribution, or even some bit string from a computational measurements result, or a optimal quantum operation represented by a bunch of gate sequence, or even a general quantum operations here. So this, in general, is how the quantum neural net works in principle here. So then let's talk about what generative quantum machine learning really do here. So our goal here is to model the distribution underlying a given finite set. So here our given finite set is just sampled from a target distribution of the quantum states. And we just want to model the distribution and to learn the distribution here. So for this targets, there are a bunch of existing models to do it. The first is a very known work about the quantum generative adversarial networks. It is also inspired by the classical well-known work of GAN here, generative adversarial network, and generalized it to the quantum case. And it's also implemented in the experimental platform. Another very well-known result is a quantum circuit board machine here. And both of us can do some tasks in the generative quantum machine learning, and I will just discuss later when we really touch it. So there are also some works on the QGAN here. For example, people use QGAN to learn either a pure quantum one single qubit pure state or a mixed single qubit state, and to use the QGAN to model the corresponding distribution in the computational basis here. And later in experiment is generalized to multi-qubit cases on superconducting platforms. And it can also be utilized to load some classical distributions onto the specific quantum states here. And here you can see that all the previous work about the QGAN here is really about to learn a specific quantum state, either pure or mixed state. So in principle, although this is a natural way to consider that a mixed state is a quantum generalization of a classical distribution here. But later I will show you that our work really want to do something different and more complicated here. So after the introduction, I hope everyone is clear about it. And then I will go to the design and the training strategy of our QuDDPM model here. So let's give a brief review of classical diffusion models here. So what classical want to do is to find a map from white noise to the distribution of true data. So imagine you have a distribution of some figures you want to generate, like for example a bunch of figures or all of it describing a cutie cat, and you want to let the computer to learn it and to generate other figures that also shows a very cute cat here. So how can the classical diffusion model do it? So first, classical people think about, okay, if we are given a bunch of these figures, then easy way is we can just add some Gaussian white noise to it. And so from the left with a perfect figure and with increasing the noisy level here, finally, we will just end up with a pure Gaussian white noise. There's no information inside it. And the forward process can be described by this by a SDE, stochastic diffusion equation here, where F is the original data and GT is just the DW, and GT describes the level to be added of the Gaussian noise, and the DW is just the Gaussian noise terms here. And for the backward process, okay, then we can just sample some Gaussian white noise. It's very easy in classical case scenario. And then we will just train and to develop and train a classical neural network such that it will learn this score function. And with these things, it will show us a way to reverse the forward adding noise process, and it will reverse Gaussian white noise backward to some corresponding figures following the specific classical distributions here. And it's just a reverse SDE here, and it will be a map from the noise to data here. And it's a very simple idea, but it really works, and it achieves a predictable success in the whole classical machine learning community here. And the advantage of this classical diffusion model here is that it does not suffer from the classical adversarial training problems that I will cover later. And there's also a lot of very successful products of the stable diffusion, DALI2, etc. here. So this is also provides us some inspiration about how to design a quantum diffusion model to do generative quantum machine learning here. So next, I will just come up with the general formalism of our quantum QuDDPM model here. So our task is about, we are given a finite number of samples. Like this S0, it is a finite set with includes some quantum states psi k, and it follows a specific distribution of E0 here. And our task is to try to generate some new elements. Also, samples follow the same distribution of E0 here. Here, there's a very important point that I want to make, is that our task here is very different from the generation to generate an average mixed state. So for example, you can consider that from a single qubit computational basis, you can, with equal probability, then the average mixed state is just the fully mixed state, which is proportional to the identity matrix here. But you can also choose another set of bases, and its average is still the mixed state. And even if the samples of the states are not orthogonal, you can still try to find a way to make their average to mixed state to be the fully mixed state. But their distribution is actually quite different, and so they are not meaning the same thing, but although their average is the same things here. So that's the first point I want to point out, that our task here is very different from just to learn the average state. So that even you given different state, you may end up with the same average state, but their corresponding distribution is actually very different here. So our QuDDPM approach is try to learn a map from a noisy, unstructured distribution of the quantum states towards a target distribution, just like the classical learning a map from Gaussian white noise to the target distribution of classical data. Here, we want to learn a map from unstructured distribution of quantum states to the target distribution here. And from this scheme figure, I will just show how these things really works here. So in the forward part, our model will also be divided into two parts. The first part is a forward noisy diffusion process, and it's implemented by the scrubbing things. From now on, I will just assume all our input and target data are just the pure states here. So we begin with this target state, pure state here, size 0, and it will undergoes a scrambling unitary UI here, U1 here for the first step, and it will output another psi1 here. And we will just go through this process with increasing strength of the scrambling power. So until the end, you can imagine that we will end up with a random state following higher random distribution, where higher random distribution is just describes the uniform distribution of quantum state on the block sphere in the Hilbert space. And specifically for different quantum states, psi I here, we will just implement different scrambling unitaries here, so such that the state-wise distance, or we can see the fidelity between any two states, will be changed during this forward diffusion process here. So from the B panel here, you can see that imagine we have some sample data that originally clustered around the block sphere at around the 0 state. And with steps of diffusion here, you can see that these red dots corresponding to each quantum state will be moved out from the pole and mode and try to cover the whole block sphere due to the scrambling ability, due to the scrambling unitary applied to every state on it. And finally, we will end up with all these quantum states that are randomly uniformly distributed around the whole block sphere. And that's the end of our forward noisy diffusion process. And in the backward part, we can just, our input state, we will start from the last capital T step here. And you can imagine that we will just input, because we end in the forward part, we end up with higher random states. So we can just input some higher random state as the beginning point of our backward denoising process here. And because only quantum unitary things cannot change the state-wise distance, because unitary can only maintain the state-wise distance here. So we want to implement a quantum channel here. And a general quantum channel will require us that not only the data qubits we need, but also we need some ancilla qubits to do it. And so I will just set the ancilla qubits for simplicity. We will just begin with all 0 trivial state here in a product state. And then this quantum operation for each denoising step will be a parameterized quantum circuit. And after it, we will just perform a random project measurement. So we just perform measurements on the ancilla qubits in the computational basis. And no matter what measurement results we have, we will just collect the post-select quantum state as the input for the next denoising steps here. And we will just continue this process, and until the end, you can see that initially that a very uniformly distributed quantum state on the block sphere, and their distance will be shrinked, and they will move towards the pole, and finally it will end up in this in a clustered state, mimic the distribution of our target distribution here. And this is like a general idea of how our QuDDPM works and how it's implemented. And I will just next slide, I will give you a more detailed description on how we really try to train every PQC here to enable to find the corresponding quantum operation for the denoising for each diffusion forward steps here.
Sorry, I have a question over here. Yeah.
Yeah.
Well, okay. So probably you kind of describe it in your paper, but I maybe just like somehow missed it. Just wondering whether is there any kind of like property that you assume for the scrambling unitary, or maybe they have to belong to the same class of like unitary with 2 design, 3 design, and stuff like that. Like, do you make any assumption on that, or it just works for arbitrary scrambling unitary?
That's a good question. That in our current paper, we just utilize like a very universal ansatz to implement these PQCs to enable our PQC to have enough expressivity to implement the corresponding quantum operation as we want. But if you can as you also you can notice that our forward scrambling also do not have any limitations on how the scrambling really did here. So it has to cover, so it will make any arbitrary ensembles of states finally will end up to be a high random over the whole Hilbert space here. But in principle, if you can come up with a very cleverly designed diffusion process, then you can also implement the same thing to the PQC here. And this may provide you with extra advantage in the training things. But in principle, I would expect that it will be pretty challenging, and it also may require that you need to have some prior knowledge on the target distribution for how to design this diffusion and backward PQC here.
I see. Okay. Yeah. I think that they're just some basically you guys just provide the framework, and then now it's for us to go and try out different kind of union trees and kind of probability distribution and test how well our algorithm work. Okay, thanks.
So our training strategy is like this. So first, suppose we want to train suppose until the K step, K+1 step, we already completed the training from capital T to K+2. And now we want to train the U tilde K+1, which is a backward PQC here. And so the thing we want to, and we will have some data, input data for the PQC here, and all zero state for the ancillaries. And after these measurements, we will collect a bunch of quantum states here. And then we want to compare this psi k tilde, the output state from the PQC, to the true quantum states under the forward noisy process, psi k here. And so the psi k can just be obtained from a forward diffusion process, while the scrambling is very easy to implement it. And then we just need to compare these two via a loss function to calculate this, like a distance measure to compare to measure the ensemble distance between these two ensembles of state sk tilde and sk here. And then we will just minimize this loss function, and it will tell us how to update the parameters in this PQC here. And after this training part, we will just keep this PQC fixed and move on to the another PQC that is the forward step as U tilde k. And we will just repeat this process over and over again until we reach U tilde 1 here. And after U tilde 1, it means that we already completed the training for all of this backward PQC here. And until now, we can just implement input high random states from the end of this, from the beginning of this backward process as the psi tilde t here. And we will just collect all the data from the psi tilde 0 here. And it will just mimic the distribution of our psi zeros here. And this is like a stepwise compared training for the QuDDPM. And I also want to point out that this thing is kind of very different from the classical case. That in classic, if you have some idea or some knowledge about how classical diffusion models works, you will find that they do a training to compare the data from they can collect the data from every step together and to compare all the compare to the data from all the steps in the forward process. The difference here is one reason is because that in the quantum case, after you calculate the minimum loss function in every step, you will lose the quantum states because when you do a measurement, you will destroy the corresponding the input quantum states here. So you cannot have these quantum states anymore in the future information processing here. And that's one reason we have to do the statewise, we have to do the stepwise training, one step by one step. Another reason is that the classical people can do like to collect the data from every denoising steps and to compare every data to the diffusion steps. And they can do one reason is because they have a very beautiful mathematical description of it. And they can come up with a lot of many different kinds of score functions which can be easily calculated and efficiently evaluated. But in the quantum case, our loss function is unlike the score function in the classical case, and it does not have an analytical description of it. And that's why we need to use a training to mimic the denoising process instead of like classical people. They can just use a score function to write out the reverse SDE here. and to just compare the score function and they can directly implement the reverse process by analytical guarantees here. So quantum KR, we have to use numerical training and to mimic the denoising process here. And that's the two reasons we have to do the state-wise training. So you may see that it's not very efficient that you have to do one step by one step, but this is the necessary things we need to do with our QuDDPM here. And also here in the following, we will just denote our forward scrambling circuit U here to be our forward scrambling circuit. And our backward denoising circuit will be du tilde here. And then I will explain what is the choice of our parameterized circuit architectures that I also question?
Yeah. So can you go back to the previous slide? I just want to kind of like understand a bit more about the training process. So say now you have a state sample from like S0, right? So you just like feed forward to, for example, now it's the K step. And then you have the backward step, right? Then you just random sample from a noise state, interact it and feed forward. For the first step, like at the T step, you measure it. Just now you mentioned that you are just don't care what is the like outcome of the ancillars, right? You just like keep people towards like the K steps, right? And basically you kind of like get an exponentially possible like kind of like state that you can explore like through this like K step measurement, and then you compare it with the exact state, right? And because now once you make the measurement, the state is already gone, and then you have to repeat the process in order to collect some kind of statistics, right? Yeah, right. So like basically what it means is that each time you rerun the whole like the training process for the K iteration, you would like get a different kind of new state, the size, user K each and every time, and then you compare it against with the exact state you need. But then the overall statistic will kind of like steer you towards the result, the training that you want, that like to get the optimal U data that you hope for. Am I correct to say that? Okay.
Yeah. Even though they are different, but we are not comparing exactly to match every state to every state from forward process to backward process. We are just trying to match their ensemble distribution here. So even they have some the fluctuation in the state state level, but it's accepted. We just want to match the ensemble here.
Right. Yeah. So it's a bit not intuitive for me to think of that, because like typically I thought like the measurement will just like bring your state to some other places because it's projections, and then suddenly it just collapse and then it just become another state. So I'm kind of like quite surprised to see that this kind of training process will give the overall trainings of the ensemble. So it's kind of interesting to see this work. Okay, yeah, thanks.
So currently we are for our forward diffusion circuit, we just take the first scrambling model where it will for each diffusion step it will include first general single qubit rotation composite of RZ, poly Z rotation, poly Y rotation, and poly Z rotation. And all these rotation angles we will just uniformly sample it from a range that we can be tuned such that we can control the diffusion level, the scrambling power and the scrambling strength of it. And for multi-qubit case, especially, we will end up with like a RCC rotation over all the pairs of qubits. And these things will introduce extra scrambling between different qubits here, if you are considering a multi-qubit space. And in principle, this is just an ansatz we chosen here, and you can just choose other ansatz to do the scrambling as well, to do the scrambling process, as long as it can implement to scrambling the information from localized qubits to the global systems here. And for the backward process here, we just utilize a hardware efficient ansatz, very well known in the variational quantum algorithm area, where we have n qubits and n ancillas, and we will just have in each layer, we will have some Rx and Ry rotations, and followed by some CC gates formed in the brick wall fashion. And repeat this for L layers in each PQCs here, and we will just end up with some computational basis measurements on all the ancillas. And no matter what bit stream we obtain from this measurement result, we will just collect the post-measurement state as output for this PQC here. And this is the architectures we utilize here. And as you may, and we also discussed that previous in a few slides before that this can be freely chosen to other answers if you prefer. And as long as currently we believe that as long as it's universal, it should achieve the similar performance here as our choices. And a key question to address here is what is the choice of the loss functions to enable the training of the PQCs here. Also, it's about how to compare two different ensembles of quantum states for their distance. So first, the idea is we come up with is a MMD distance. And I will just begin it from the mean fidelity definition here. So suppose you are given two ensembles of quantum states E1 and E2 here. And the mean fidelity we define it to be the state-wise fidelity from every pair of the quantum states in E1 and E2 and their average here. So you see that suppose phi is sampled from E1 and psi is sampled from E2, and their average fidelity among all the combinations is we define it to be the mean fidelities here. And next, we will introduce the maximum mean discrepancy distance here. So the MMD distance is defined to be first is F1, the distance of the mean fidelity of E1 itself plus the mean fidelity of E2 itself, and minus two times the fidelity of mean fidelity between E1 and E2 here. So first you can see that once E1 equals to E2, this MMD will definitely be 0. And also you can imagine that the first term will describe the radius between the radius of the first ensemble E1 here, and E2 will like a description of the radius of the ensemble E2 here, and the last term will describe the distance between the distance between the two ensembles here. And this is how we define MMD distance. And it also shares the same definition as the classical statistics. Although in classical statistics, there is no fidelity definition. They use some other distance measures to measure the distance between the classical data here. Property of this MMD distance is that it's very easy for calculation, but sometimes it may fail in some specific distribution, as I will just cover in the next slide here. And this is a very good distance measure, and we will utilize a lot in our simulations here. And so with this MMD distance, our loss function, suppose this EK is the target noisy distribution at K step, and E tilde T here is the input for the whole backward process, and the UL tilde is the backward denoising PQCs here. So we will just define our loss function for these things to be the MMD distance, where EK tilde can just be seen from the previous slide that is a function of all the inputs backward denoising PQCs from the capital T step to the K+1 step, and the EK tilde is the distribution we want to is a target noisy distribution we want to match here, and this is the MMD distance. And the next distance I want to cover is one-sustain distance. It's a more complicated distance and got the idea from the optimal transport theory, which is a classical well-known theory for statistics and economics here. So first, I will begin with a lemma that why we need this one-sustain distance. So suppose you have a U1, which is a uniform circular distribution on the Bloch sphere. For example, if you perform a RY rotation, poly-Y rotation uniformly on a trivial state like a 0 state, and you will end up with all the quantum states lying in a specific ring on the Bloch sphere. And E2 we assume is to be a hard random state distribution on the Bloch sphere. And then you can just follow a simple calculation. You will find that actually the MMD distance between E1 and E2 is simply 0. So that means that even you have two very different distributions. You can think about that E1 is only a one-dimensional distribution, but E2 is a two-dimensional distribution. But distances, MMD distance actually 0. So using MMD distance, you cannot discriminate between these two ensembles. So that's the reason that we need some other measures to measure their distance here. So that's why we introduced the Wasserstein distance. So Wasserstein distance, it comes from the optimal transport theory, and is also several years ago is also imported into the quantum area. So, and share the similar idea as our work here. So first, this figure is about what is optimal transport classical theory do here. Suppose you have a distribution Px here, and you have another distribution Qx, where Px is like a prior distribution, and Qx is a target distribution. And so, and you will have a cost function that will measure you from moving from Px in a specific point to another point Qy here. What is the corresponding cost? And the optimal transport theory asks you, what is the corresponding transport plan that you can change the distribution from Px to Qx, but with the minimum cost? And that is called the so-called optimal transport here with the minimal cost for it. And so in the quantum case, we will just consider it to be like, first, the d squares here, we will just use it to be the trace distance. And for pure state, it will just become the infidelities here. And pi here will become like the capital pi here, big pi here will be like the set of all the distributions, where its marginal will follow, marginal distribution follows the corresponding prior distribution E1 and the target distribution E2 here. And so we will just utilize the d squared infidelity here as like a cost, something like a cost measure in the classical scenario. And then when we minimize this OPT here, we will end up with a minimum cost. It will give you a description of the corresponding distance between the distribution E1 and E2 here. And that's our definition for the Wasserstein distance for the quantum for the ensembles of quantum states here. So these things in principle is very hard to calculation. But luckily in the discrete case that where E1 and E2 are just some discrete, like a discrete set of quantum states, then this discrete set of data here, then this OPT calculation, this minimization things can be cascaded into a linear program guaranteed by the classical statistical theories here. And although it's still hard for calculation compared to the MMD distance, but in some cases, as we mentioned in the lemma 1 here, it is necessary to utilize this Wasserstein distance to discriminate between the two ensembles of quantum states here. And after the introduction of the loss functions here I will just introduce the benchmark I mentioned earlier about we compare our QuDDPM. So the first candidate is a QDT here. We call it quantum direct transport. And it's just a direct generalization of the quantum circuit board machine here. So for QDT here, we will input with a bunch of, as you probably know that quantum circuit board machine is targeted as following, that you input with a trivial state like an all zero state. And you want to learn a quantum unitary such that your output state will match you can measure the corresponding probabilities of your output state in the computational basis, and you will get corresponding probabilities here. And with this probability distribution, you can compare it to the target classical distribution. And your idea is try to load this classical distribution onto your output state. And this is how the basic idea of the quantum circuit board machine. And we generalize this idea to how to do the ensemble learning here, while we still input this, the input state we will assume is to be sampled randomly from the higher distribution. And we will still begin with some SELs in the trivial state. And PQC here will be a very long PQC here for fair comparison here. And after this unitary here, we will just still perform some random measurements on the SELs, and we will collect all the data here. So these things, and then we will just compare the output state towards our target distributions and to minimize the loss function and to update all the parameters in the PQCs here. So here you can consider it's just like to collect all the PQCs in the classical diffusion model, in the quantum diffusion models together to a whole very big unitaries here. And we just want to learn it. You will probably already have the idea that these things will be very challenging to train and may not have a very good performance here. And this is a QDT here is a generalization of the quantum circuit machine when you want to do a learning for like ensemble of quantum state instead of a single quantum state here. Another work we want to compare is the QGAN here, the quantum generative adversarial network. So these things will include two parts you need to train. The first part is called the generator, and the second part is for the discriminator. The idea for the GAN network is because that initially people think that it's very challenging to measure the distance between two ensembles of data. So they came up with the idea that how about we replace this distance measure by a discriminator, such that if finally our generated ensemble is very close to the target ensembles here, then the discriminator will fail to tell the difference. And if we can train the generator and discriminator vice versa, that we train the generator first and then go to discriminator and then go back to generator and then go to training the discriminator, then finally we will end up with a perfect generator that will fully fool the discriminator, such that the discriminator cannot tell the difference between the generated ensemble and the true ensemble. And this just means that we already learned the target ensembles here. And this is the basic idea of the generative adversarial network here. And for this QGAN here, QGAN is also originally developed for only to learn either a single quantum pure state or a single quantum mixed state. And here we generalize it to learning an ensemble of quantum states here. So we still begins with a hard distribution and hard random state as input state and with ancilas and with a very long generator here and goes through this distribution. And we will have collect some output state. And then we will, first part, we will just train the generator to minimize the loss function for the, then we will have the output state of the generator goes to a discriminator. And also, and let the discriminator to check whether our input is a true input, the data comes from the true distribution or comes from the distribution are generated here. And the first part is about to minimize the loss function for the generator. So we can first optimize the generator while holding the discriminator. And after this part, we will have a little bit better generator for this discriminator. And after it, we will just hold this generator to be fixed and train the discriminator by optimizing another loss function LD for the discriminator here. And so we will repeat this training loop for several times until we reach the training equilibrium point for the training here. And after it, we will just collect all the states generated from our generator here and discard the discriminator, and as the output ensembles learned from by this QGAN scheme here. And this is the two schemes that we want to compare. And for fair comparison towards the QuDDPM here, we will keep either the training the layers of quantum circuits or the number of training parameters in the PQC for the QDT here, and the generator for the QGAN here to be the same number as the total number of parameters or the layers of the quantum circuits in our diffusion model for fair comparison here. And that's the comparison candidates here. And in the following, we'll just go through a benchmark to show the advantage of our diffusion model compared to this either the quantum direct transport plan or the quantum generative adversarial network model here. So this training things is that I will show our training history and a distance measure here for the training of the QuDDPM here. So first, our target ensemble is a very simple toy ensemble. It's like a 2-qubit state that is clustered around as a 0-0 state. So it's just like a perturbed states from the 0-0 point. And you can first see the diffusion steps from the top that we will begin with 20, which is the last step of the diffusion, which is also the first step of our backward denoising process. And at the beginning, you can see that our QuDDPM here, due to the random initialization of the initial parameters, will have your output states will be the same number as the total number of parameters in the QQC for the QDT here. And at the beginning, you can see that our QuDDPM here, due to the random initialization of the initial parameters, will have your output states well, from the first step backward, PQC will have a very large distance compared to the true distribution. Here you can see the y-axis is measures the distance between MMD distance between the ST tilde, which is the generated ensemble quantum state of the T step, backward T step, and E0 is the initial true distribution here. So with the training goes on for this PQC, our distance will decreases and reach to a minimum point for this specific PQC. And after this training, we will hold it here, hold this PQC, and then go to the next denoising step. And due to the random initialization of the next denoising step, the corresponding distance, the distance measure will slightly increase towards another point. And then we will train the second denoising step, and then the distance will decrease again towards another minimum point. And we will just repeat this process through the whole denoising process. And until the end, you will see that at the last step, our denoising the MMD distance between our generated ensembles compared to the target ensemble is very small, very close to 0. And actually, we reach to the accuracy, the precision of 0.002 for the QuDDPM here. And all the blue dots, all the green dots, the red dots is the corresponding denoising, the forward diffusion data here. So you can see that initially from 0 and finally it will end at 20. Also, you can see that from the diffusion that all the data ensembles actually have a larger distance compared to the initial state. And the green dots is the testing data that the input state, the input hard random state for the testing is actually another set of randomly sampled hard random states. And it has never been witnessed or used in the training of the PQCs here. And you can see that we can still achieve a very similar performance compared to our training here. Also suggests that we have a very good generalization abilities for our QuDDPM model. And for comparison here, you can first see the gray lines, which is the QuDT model, a generalization of the quantum circuit machine here. So initially, because of the random initialization, the initial stage of the distance will be similar to our PQC here, but it will very soon to jump to a specific minimum point. And due to this is a very long and very large circuit model, it will be very hard to train and easily to start in the barren plateau. And that's because the MMD distance can only fluctuate around 0.2 and end up with nothing improvement in the whole training, in the late training history here. And for generalization here, for the testing data, it just have a worse generalization ability reach to the MMD distance of 0.4, meaning that they are actually very different. And similar things also happens for the QGAN here, that initially very close, and this undergo some decreases process, but it will just still also stuck at some point and then without any further improvements, and also end up with a very good generalization abilities here. And this is like a benchmark comparison for our QuDDPM model towards the previously known QDT model or the QGAN model, to show that our advantage of our model in the training and in the generalization abilities here. Yeah, for the ensemble learning. So after this benchmark as a toy example, I will go to some analysis for the complexity of our QuDDPM and the convergence analysis of the QuDDPM here. So first, we can consider about the gate complexity of our QuDDPM here. So imagine that you want to enable enough expressivity of this whole quantum circuit models here. So which means that you need a T design here, and at least a T design for this whole circuit. And you know that the T design model needs to can at least be achieved by a polynomial number of quantum layers of quantum gates in the quantum circuit. So that means that if you count the total number of quantum gates, you will expect that the total number of quantum gates in the forward scrambling process will be in the scaling of n squared, where n is number of qubits for our data here. And then, so we also want to implement implement efficient training, which means that we want every PQC does not suffer from the barren plateau phenomenon, where the variance of gradient of the training loss function will be exponentially suppressed versus the number of qubits here. So which means that we want our to avoid this barren plateau phenomenon. The easy way to do it is to use a very shallow circuit to do it. So it's widely known that for the global loss function, we can have the depth of the circuit to be in the log depth of this respect to the number of qubits in the whole circuit. So, and if you want to have log depths for each PQCs here, so then, and also you want the whole circuit to be very expressive and very powerful. Then you have to have the total depths to be polynomial here. So you can get an estimation of how many different steps we really need here. And you can find that it will be the n over log n here. So it is still manageable, and but you just add a better, more different step, although it means more PQCs you need to introduce and more measurement introduced, but you can guarantee a better performance and a better training here, as this T here will, as their T has some interpolation between the prior distribution towards the target distribution, or from the noisy distribution back towards to the target distribution here. And also for each PQCs here, as we point out before, that is a quantum, it's trying to implement a quantum operation or a quantum channel here. So we know that the maximum number of epsilons for n qubits system for a quantum channel is to be the epsilon number can just be smaller than 2n here. So in principle, so that means that in principle we can have our PQC to be at most for each step it at most 3n number of qubits. So it's still just a constant times the number of data qubits here. The number of data qubits, so it's still a very manageable resource here. And to analyze the error in the learning of our QuDDPM model, we can consider it includes 3 parts. And it's also this idea is also proposed for the classical diffusion model in a recent paper here. So the first part is about the error in the diffusion, which describes that the deviation of our output states ensemble from the forward diffusion process compared to the true hard random states. That, as you know, that a hard random state is actually requires that the exponent arbitrary t design here for arbitrary t here. So it actually will requires exponential number of layers here. So that will introduce an error that for our deviation of our generated ensemble, our noisy ensemble toward compared to the true ensembles here. And here, this result we can obtain it from the very well-known analysis of how the random quantum circuit implement a T design here. So you can see that this error will be exponentially, where here the k is the corresponding corresponding, we call it T design here to avoid misleading on the notations, we just call it K design. So how many moments or how many K design we want here is the K here. It requires, this is error for the K here, and the T is the corresponding diffusion steps. So you can see that this diffusion error will be exponentially suppressed by the number of diffusion steps. So which also supports our conclusion before that the more diffusion steps here will involve a better performance and leading to a smaller error here. And the second part is about the measurement error. That, for example, if you have 2 constates, no matter you use the MMD distance or you utilize the Wasserstein distance, first thing you need to do is to compute the fidelity, the statewise fidelity between the states from the 2 ensembles, target ensemble and the generated ensemble here. And to calculate the fidelity, a direct idea is to use the swap test. And the swap test measurement is based on probability measurements on the ancilla qubits. And these things will introduce an error due to your finite number of measurements here. And here, from a very simple calculation, you will see that suppose we have n data here, and small m is the number of measurements in performing each swap test here. And this is the measurement in estimating the mean fidelity, the measurement error will be suppressed by 1 over n divided and the square root of m. And the last part is the key point that people usually cares a lot in the quantum machine learning, also in classical machine learning, which is about the generalization error. Generalization error is defined by, we suppose we have a loss function, and E0 is our target distribution here. U tilde is a trained unitary PQCs here in the backward process, and ET tilde is the true hard random ensembles, the true hard random states here. And the ST tilde here is some hard random state that we sampled from the hard random distribution here. So the generalization error will measure the difference between the arbitrary hard random states, the loss function, compared to the states ST here that you used for training here. So it will measure the generalization ability that when your quantum machine learning model are faced with some data that you have never, although they come from the same distribution as your training data, but this model have never seen it before. And how is the error, whether it will introduce whether a large increase in the loss function or very small increase in the loss function here. So if the generalization error goes to 0, it means that you goes to the perfect generalization abilities here. So we still have this definition here, and I will just, in principle, it's a very hard analysis in analytically. So we just provide some numerical insights to it. So here we consider still a clustering states learning model here, toy problem here, and we show the generalization error here compared to the number of diffusion steps, and and n is the number of data here, the number of training data here. So you see that for the increasing of the t here, the generalization error decreases due to a precise interpretation between the noisy distribution towards the target distribution. And the more data indicates that you provide extra information to the model about your true distribution, and it also guarantees that you can have a better generalization ability. And specifically, we can do a linear fitting for it, and we find that it actually is just one reciprocal principle, inversible distribution here. So the generalization error will be proportional to one inverse of the number of diffusion steps and the inverse of the number of data here. And previously known result in the generalization error for general quantum machine learning model without any assumption here is that the generalization error here is proportional to 1 over square root of n here. So our error here is still within this range of, and also provides some extra advantage here. Also, a detailed explanation and understanding for it, we will just leave it for future work. And after all these theory things, we will come up to the last section, which is about what can we do with our quantum diffusion models here, and is there any interesting applications for it? First things, we still begins with the cluster state, that is like a single state, that is some quantum states around the arbitrary fixed quantum state. And for simplicity, we just assume just a cluster around all 0 state. And you can see that the red line is how the mean average fidelity compared to 0 decreases with the number of diffusion steps. And the training and the testing is showing that you should read it from the right to the left to show how the mean fidelity increases with the number of denoising steps. And it has a perfect alignment with respect to the diffusions here. So meaning that they almost learn the same distributions here. And the last figure is for 1 qubit, a very simple case. And the second part is for the 2 qubit case, which is also shown in the previous benchmark plot here. And to show how we learn the cluster states here. And this is a toy problem. And if we come up with some more complicated cases, first thing we can do is to learn the correlated noise here. So suppose we are given such a following states, which is a 2 qubit state, includes C0, 0, 0, and 0, 1, and 1, 1 is occupied in the 3 different bases. C0, C1, and C3 are some fixed number, complex numbers here. And we will have a probability of either P or 1 minus P. This state will undergo an error of either XX rotation or ZZ rotation. So it's a coherent noise and correlated noise. And we will assume that this P is fixed, but the rotation angle delta here will be a uniformly distributed within a range from minus delta 0 to delta 0 here. And we can vary the average fidelity of the noisy states with respect to the whole distribution, with respect to the whole distribution here in the computational basis of 1, 0. And from the average fidelity, we can infer another probability about what is the corresponding correlated noise error, corresponding correlated noise probability here from the following formulas, from the following calculations here. And this is the first example we want to do here. Another example we want to do is about phase learning in the many-body physics systems, which is very interesting for many physicists, the condensed matter physics. We consider a toy model for the transverse field Ising model here, where its Hamiltonian is described by the ZZ coupling on nearest neighbors plus transverse field in the X here in every single qubit. And for G smaller than 1 and greater than 1, it will have two different phases. The first, when G smaller than 1, it will have the ferromagnetic phase, but G greater than 1, it will be paramagnetic disordered phase. And the magnetization can be measured by this the following operators here. And we see here that, and specifically at G equals 1, it will be the critical point. So we want to learn is to give our target distribution to be some ground state of this TFI following the ferromagnetic phase. And can we learn a map to map the hard random state towards quantum state also enjoys a very large magnetization here. And so here, first we can show that for the correlated noise learning here. So you can see that previously we have this formula that the inferred probability and the correlated noise probability is directly proportional to the F10 here, average fidelity F10, and all the rest is just some constants here. So once you have this information, you can have once you have F10 learned accurately, you can infer the error probability very accurately. So we have the correlated noise learning here that our beginning initial state will be the noisy state under the either XX rotation or ZZ rotation for the specific fixed state. And with the increasing of the diffusion process, it will goes towards a higher random value described by the red line. And for the blue and the green lines, it shows that the training and the testing data which sampled from the higher random state, and we will end up with a similar F10 average fidelity here. Shows that we can, and then from the similar F10 average performance on the output state of the QuDDPM, we can then infer the error probability of our correlated noise here. And the second example is about the many-body phase learning here. So diffusion at the red dots we show here, we do not show a diffusion process, but we show the distribution of our target the ensemble of quantum state for its magnetization here. So at t equal to 0, described by these red lines here, it is corresponding to the ground state we sampled from the TIFM in the ferromagnetic phase. So you can see that it has a very high distribution, it's almost all the quantum states have a very high distribution, have a very large value of its total magnetization here. And you can shown by this red line here. And through the diffusion process, we will end up with some higher random state. And then the distribution of the magnetization will have no information, like no prior information about the ground state of TFM. And it just look like a normal distribution here and has centered at around 0.5 with no increment to either paramagnetic or paramagnetic. And then in the blue and the green lines, we show our training and testing results that on our QuDDPM. And you can see that it has, for the small magnetization, it also almost have nothing overlapped here. And almost all of its generated state have a very high total magnetization here, around 0.8 or 0.9 here. And it's also very close to the diffusion here. Although it does not have exactly the same as as the ground state of the TFM here, but it also already generated a lot of quantum states that always have the same high magnetization here, showing that they are in the ferromagnetic phase here for the many-body phase learning. And the last example I want to show here is a very favorite, it's almost my favorite example I want to show for this QuDDPM model here. So as we mentioned before, that the circular ensemble of quantum states cannot be learned by the MMD distance, because it's the MMD distance between the circular quantum states here with just in the Bloch sphere formed a circle here, single qubit states. And it has zero MMD loss compared to the training of this, compared to the higher random states here. So you cannot use MMD distance. That's why in this example, we will use Wasserstein distance to do this training here. And first we can see the red part for the forward denoising diffusion process. A circular ensembles of a quantum state initially forms a circle in the Bloch sphere, and through the diffusion process, it will be diffused around all the directions, and finally it will uniformly cover the whole Bloch sphere, look like the A3 plots here. And in the backward training process, we will begin with the higher random states that cover the whole Bloch sphere, and through the whole QuDDPM, and we will end up with the backward, we will end up with a target output generated distribution that almost always lies in the target circle we want, although there are some small tiny fluctuations here. Although most of the quantum data lies in this circle. And the same phenomenon, we can also see it from the testing data, that we begin with another set of higher random states, and we can end up with the similar performance in the final generated ensembles here. So this shows that we learn this, how to learn a quantum map from the higher random states toward a specific topological structure for the quantum states, quantum ensembles here. And also we can show its performance benchmark via the expectation of poly-Z operators here. For the circular, because we generated these ensembles of circular distribution via a single poly-Y rotation on the trivial zero state. So its poly-Y expectation will simply be zero. And we can see that in the first part, we show the training process for the training data set, that it has a perfect alignment in the Y expectations from the higher random states will have an expectation at around one third, but finally it will end up to the value of very close to zero. And in the E plot, we show the testing data from another higher random ensembles of higher random states, and it also has a very similar performance compared to the diffusion process, and end up with zeros here. So that shows that that's also a quantitative comparison for our diffusion process and the backward denoising process here. And after all these applications, I will end up with like a discussion in our QuDDPM model here. So our model is the first time to provide an explicit construction of quantum diffusion and denoising our quantum data with loss functions, training strategies, and error analysis. Although there are also some, after we completed this work, we also get known that there are some other works also in the diffusion idea, but they are doing classical diffusion and on the quantum classical diffusion and quantum denoising process here. And they may share the similar idea, but our model is the first time to show that via the quantum diffusion and the quantum denoising, and with full design in the training strategies, error analysis, and plenty of numerical simulation results here. And there are also a bunch of future directions we want to discuss and cover in the future. First is, although we have already came up with two different design of the loss functions, the first part is the MMD distance, and the second part is the Wasserstein distance. But all these distance measures are based on the quantum fidelity measure. And for quantum states with many qubits, swap test is not very efficient to implement, as it requires a control swap operation on two quantum states. So we need to come up with some extra designs of loss functions that is more efficient and more capable for experimental implementation in the near future. And also it's an idea about currently we just do diffusion to diffuse any arbitrary target quantum states and ensembles towards the higher random state over the whole Hilbert space. Although it's very easy to implement, but in principle this diffusion can make the learning not very efficient, and you need to learn a quantum operation to shrink the distribution of ensembles or quantum states from the whole Hilbert space towards your target. So a better idea that could be to use some control diffusion that you can control the direction and the diffusion level of the forward diffusion process. Possible idea is to enhance the symmetry of your target distribution and to try to do the diffusion only within a subspace of the whole Hilbert space instead of to cover the whole Hilbert space here. And also our QuDDPM can play a role in other quantum technology and engineering tasks, and also for some classical data generative learning when they are encoded into the quantum area. And that's all for my talk here and for our work. And if you have further interest, you can I attach the QR code for our paper and a code and the QR code for our numerical simulation code and we post it in the GitHub. And you have further interest, you can take a look at it. So I will end up with acknowledge about my collaborators, Peng Xu from UIC, Professor Xiaohui Chen from USC, and my advisor, Professor Xintao Zhang from USC, and also for the funding agencies. And thank you all for your listening through the whole talk, and I'm welcome to any questions here.
Cool. Yeah. Thanks, Bingzhi, for the very, very interesting talk. And yeah, it's to summarize everything very nicely. And for the audience, if you have any questions, feel free to unmute yourself. I think that Tinti have some questions. I see you
yes.
Yeah.
Yeah, thank you. Thanks. Thank you for the very nice talk. I just have a very quick question. So in terms of the many-body, learning the many-body phase, how does the system scaling look like in terms of your approach, and how large can your system go? And if how large can your system go? And if it cannot go to like very large system, what will be the difficulties for your approach?
Here our numerical simulation here is about 4 or 6 qubits for the data side, and because our implementation of numerical simulation of our diffusion model requires an extra number of ancillas here. So due to the ability of the classical computer, we can really not go to very large system. But in principle, I believe these things can do in a medium size, at least in a medium sized system, and as long as you have the ability to implement it.
Okay, I see.
Training is not really a problem here because we have efficient training guarantees for as long as you have enough number of diffusion steps. So basically the challenging is about really how you can implement a large quantum system simulated on a classical computer.
Okay, thank you.
Yeah, maybe other people's thinkings about their questions, if I could like simply ask one. So over here, yeah, especially on the left one. So over here you can learn about correlated noise, right? Like just basically the question is just kind of related to this one is about the decoherence, because over here you are kind of like actively injecting structural noise into your systems and then trying to use diffusion and kind of decoding in order to get back what you want, right? But now it's like, what if like you have some kind of decoherent noise? How would that affect the kind of performance of this algorithms? And if there's an effect, and how would you be able to counter, like, could your algorithm learn about this decoherent noise?
You mean you ask if
Yeah, just
the noise itself is correlated. I mean, depolarizing noise or
Yeah,
the
depolarizing
circuit.
noise. Yes, yeah. Just like assuming now you are implementing
I see.
your hardware, your algorithm on a noisy hardware. Like, how would that affect it? Or whether like your algorithm can learn about this decoherent noise and trying to bridge it back to the pure state example that you have.
Well, that's a good question. That the depolarizing noise itself will make your, even if you start with a pure state, depolarizing noise will directly make your ensembles that you want to learn to become a mixed state ensemble. And that's currently out of our reach for this work. But
Yes, of course.
we will definitely list it into like the future direction about how to learn ensembles of mixed quantum states with the diffusion models here. But I believe that there should be an approach to do it.
Yeah, for sure. Because like now I see, okay, so for example, the classical shadows, they also utilize some kind of like structured randomness in order to extract information. And this is like exactly how you did it. Yeah, just wondering whether this kind of approach can be used to counter some kind of unwanted noise that is inject into the system, not on our will. Yeah. But in any case, it's just for future direction possibly. And could you go to page 24?
24. Yeah.
Yes. So on the results, like what is the standard deviation represent? Like why do we have such a large standard deviation as you progress on figures D and E? D and yeah, the standard deviation. Yeah.
You mean this part? Or
Yeah. So I guess there's a standard deviation, right? Like what does it represent, and like why the standard deviation will get kind of grows with the number of steps that you have.
Yeah, this area plot represents the standard deviation in the expectation of this y square things for the output state as the backward denoising step at the t step. So initially, because you begin with hard random, so it has a very large fluctuations here. But finally, with the backward denoising steps, this standard deviation will be shrinked, and finally it will be shrinked in a very small values here. And specific numbers we just listed in the papers.
I see. Okay, got it. Okay, yeah. Okay, yeah. I think we overrun the seminar for quite a while, but thanks, Bingzhi, for staying up like quite late in your time to kind of like present your work and answer our questions. Maybe we can end our seminar now. I believe like people like audience that have questions, they will shoot you questions to an email so that you can answer the questions like offline at any time you want. And thanks again, Bingzhi, for the very interesting talk, and see you guys next time. Yeah, bye.
Thank you for the invitation, and thank you for all of you guys. Thank you. Bye.
Yeah, thanks. Bye.